Alright, so good day, dear teachers, professors, and students. So welcome to the next lesson in our series of videos narrating the story of the binomial theorem, inspired by the narrative of J.L. Coolidge. In this video, we will explore the second form in the story of the binomial theorem. We call it the Newton-Raphson method. And here is the general iterative formula. So this formula provides an approximation to a root of a function, cubic function, or quadratic function. In the case of square root approximation, so we let f of x is equal to x squared minus a in order to solve for the square root of a, right? Okay. And then this function or the square root application using the Newton-Raphson method recovers the Babylonian method as a special case. Okay, so I will leave it up to you to derive it. But of course, I'll show in this video how we derive the Babylonian method or the Heron's method using the Newton-Raphson method. Again, please take some time to work through this derivation at your own pace. But I will give a glimpse of the derivation of the Babylonian square root approximation based on the Newton-Raphson method for a deeper appreciation. Alright, so shall we? Alright, so we begin with the Newton-Raphson or Newton-Raphson iterative formula, this formula. And then for our function, we have x squared minus 8 because we are going to get the square root of 8. And the first derivative of this function is equal to 2x. So we now have f of x and we have f prime x. So as we substitute these two functions into the formula, so we have the new approximation is equal to the old approximation minus x squared minus 8 over 2x. So we manipulate this. First, we write with the common denominator, right? And then next, we combine like terms. Okay, so we just distribute the negative sign here, negative x squared and positive 8. So we have 2x squared minus x squared, we have x squared. Okay, and then we have negative times negative 8, that's positive 8. Okay, now we have simplified the numerator. Next, we separate into two fractions so we can work one term at a time. So for the first term, we just cancel x. So we have now x over 2. And then, for the second term, we divide the numerator and the denominator by x. Alright? So we now have 8 over x all over 2. Okay? Thus, we now have the new approximation is equal to x over 2 plus 8 over x over 2. And finally, we write with a common denominator of 2. So we have the Heron's formula. Okay? Wherein x, or the new approximation, is equal to 1/2 times x plus 8 over xn. Okay? And then since our area is 8, then we have 8 here. Okay? As the value of 8. And who was Heron, by the way? So Heron of Alexandria was a Greek mathematician and engineer. He was famous for his works on geometry and mechanics. He described this square root approximation method in his writings, which is why it is now called Heron's formula. And now we're going to have a GeoGebra simulation. So in the workbook, there's another example where we applied the Newton-Raphson method to the cubic function here. So please take your time and carefully go through the algebraic derivation at your own pace. But for now, for the second part of this video lesson, we will work on with an algebraic But for the second part of this video lesson, we will work with the GeoGebra reconstruction to visualize and apply the concepts of Newton-Raphson's method in a dynamic way. Okay, so let's go now to GeoGebra Classic. And then we set up the function. So we have x cubed minus 2x minus 5. Okay, and then we get the root c, this function, intersects with the x-axis at this particular point here. So let's get the value of that point. Okay, so our root is 2.09. Alright? Next, we're going to get the derivative of the function. So we have 3x squared minus 2, and we use the iterative formula of Newton. So let's have a slider first. Okay, this is the slider of iterations. Okay, and then let's, since our correct root is 2.09, so we can have 1.5 up to 2.5 or 2.1. Okay, so that is our slider for the iteration, the many iteration. And the many iteration we will be doing, the more closer we are to the root. Okay, so let's use the iterative formula. So a minus f of a over f prime of a. Okay, so at 1.5 the value is 2.47. And let's have a point, a dynamic point. So that would be v0. Okay, it's a point that would move along the x-axis, going to the root. That's our expectation. Okay, so the more iteration we will be doing, the closer we will be to the root. Okay, so let's now move the slider. Okay, see? So as we iterate, we move closer to the root. Okay. So, alright, so this worksheet shows how ancient Babylonian ideas of balancing parts of a rectangle to approximate a square side evolved through Newton's generalization into a robust, universally applicable method for finding roots. So the GeoGebra reconstruction not only simulates the iterative process, but also visually demonstrates the underlying geometric intuition that has spanned millennia. So may this blend of geometry, history, analysis inspire your own mathematical explorations. And finally, for a constructive approach to learning, please select and solve 1 out of 3 activity items here in your seats. So take the time to show your solution process and be ready to share your reasoning with the class.